Hi, my name is Bhumanand Barik and welcome to my YouTube channel. As I have discussed earlier, today we will be discussing about ridge and lasso regression. So, we have already discussed ridge and lasso regression both are used for resolving overfitting issue. So, when we are having overfitting issue, that time we need these two algorithms. So, lasso is also used for feature selection. So we will be seeing on the screen how both these algorithms work. Let's see. As we can see on the screen, data is actually split into training set and testing set. So here in training set we are representing it with red dots, and when the best fit line is applied and the model is applied, it is actually giving us correct line, which is our best fit line, and it is showing us low bias. It is especially low bias. But if we found, as we have found our best fit line in training, when we are implementing the same model into testing set, let's see what happens. So in testing, we can see here only those lines, those data were present in training, those data fall on the best fit line. There are so many other data which are present in testing also. Testing time, and those are not actually giving us good result. So simply this issue is like high variance issue. So as this is high variance issue and we were having like low bias and high variance issue, this issue is actually known as overfitting issue. This is actually overfitting issue. So when overfitting issue appears, that time we need to proceed with ridge regression. Why we need to proceed with ridge regression, I will explain you right now. The best fit line which we are having right now, which is actually best fit line for training set and which is not suitable for our testing set. In order, we can say like the line which we are having right now, it is having more stiffness. More stiffness means it is quite stiff, means like suppose this is x1 point, this is x1 point and this is x2 point. When we are making a small variation in x-axis, like when we are moving from x1 to x2, and the corresponding representation which we are calculating in y-axis like y1 and y2, here a small variation from x1 to x2 is costing a lot of variation from y1 to y2, which is actually not generalized. We can say, suppose this distance is x1 x2, this is x1 x2 distance, and here I can say like this is A and this point is B on the line. So here AB is greater than x1 x2. AB line is quite greater than x1 x2. Similarly, if we see y1 y2 line is quite greater than AB. So here y1 y2 line is extremely greater than x1 x2. So what it results, I will tell you how this is quite bad for our model. I will tell you right now. We can see here, I'll just tell you. As we can see on the screen, suppose in x-axis we are having experience feature, which is our independent feature, but in y-axis we are having salary feature. So we need to estimate how much salary a person will receive when a little variation or some variation happens in experience. Suppose a person is having 5 years of experience, and again we found another person which is having 7 years of experience. So whether like the salary will change or not, or if it changes, how does it change, that we need to calculate. Suppose, so in this scenario what will happen, a very little difference happens. The distance which is traveled from x1 to x2 is quite little. Corresponding to this x1 x2, this AB distance is quite higher, and corresponding to this y1 y2 is quite higher. So it means a very small change in experience is costing a lot to company, because the salary higher is quite good. Here suppose 10 here 10 lakhs or 15 lakhs, 20 lakhs, 25 lakhs, like this. If it is increasing here, just for 1 year of experience difference, the salary is different, it is changing from 20 lakhs to 25 lakhs, so which is not good. Ultimately we are telling here, this model is not generalized. This model is not generalized. So here, to create a generalized model, what we can do, we have to reduce the stiffness of this graph. As the line is quite stiff, we have to reduce the stiffness. Stiffness means it has to come down. The slope will come down here, like you can see the red line or the green line which is drawn on the screen. Here the stiffness has reduced. So how to reduce the stiffness using the code? The formula is, as you can see on the screen, now the formula is sum of residuals. This is calculated in linear regression, as we have already calculated it. This is what the error we find the error, sum of residuals plus lambda value, and this is the square of the slope. This is the slope which we are finding, the square of the slope. How do we find the slope? Slope is simply found using the m value. And how do we find the m value? Using the features. So suppose our slope is m1. M is one slope we have received, we can say here lambda into m square simply. If there are multiple m value, multiple features are there, then we can say here m1 square, m2 square, m3 square, like this whole into lambda value, and the entire calculation will be added with the sum of residuals, this sum of residuals which we have already learned in linear regression. With that, it has to be added. Let's see what happens. As we know, before applying ridge regression, we know that our data set was fitting properly with training data set, or our model was fitting properly with training data set. We were getting our best fit line. It means what is our x value, similarly corresponding y value we were getting. Suppose we have estimated y value is something like this, and y cap is also like that. Suppose y value we have estimated is 6, and we got our y cap as also 6. So here the 6 minus 6 equal to 0, like that. For x2 we have received y2 also 8, and y cap 2 is also 8. So 8 minus 8 is also 0. So here ultimately I am trying to say this sum of residuals turns into 0 when we get our best fit line. But as it is not fitting test data set, That's why this additional term is added. Here lambda value is taken very small. Suppose here as an example we are taking lambda equal to 1, and m value, suppose we are considering m value as 1.2, equal to 1.2. So if this calculation is done, then definitely we will be getting something like 1.44, which will be our like the value of ridge regression. So suppose this 1.44 is the calculation of this blue line, but how do we get this green line, or how do we get this red line to decrease the stiffness? Simply we have to make the changes in the m value. If this m value reduces, then this stiffness can be reduced. If this m value reduces, what will happen? We won't get our best fit line. So this value won't remain 0. This will increase some point something. It will be something like 0.25, 0.35, like that. Definitely, because as our like here the line was like this, now the line is like this. Here it is reducing, the slope is reducing. So somehow the best fit line is not best fit right now. Somehow there are errors, some differences we have received. Definitely it won't be 0. It will increase. As it is increasing, this m value will decrease. But if it is decreasing, what will happen? I'll tell you. Even though this new line is not best fit, somehow it is like the stiffness has been reduced. The stiffness has been reduced. Now it is more generalized than earlier one. Earlier one was fitting 100% to training dataset, but it was not fitting our testing dataset. Now this new line won't fit 100% to test like train dataset. Somehow some error will appear. It is not like, even though the bias is not high bias, still it is low bias. But here in test dataset variance has been reduced. So it means earlier in test dataset we were having high variance, but now it doesn't show like high variance. It turned into low variance, because suppose here we are getting 1.44. The value is now 1.44. When we have reduced this 1.2 to something like 1.1 or more than that, the value turns into something like 1.21 or 1.30, something like that. So as here we can see 1.30 is less than 1.44. So as this value is reducing, the stiffness has been reduced. So ultimately we got a generalized model. Here in this ridge regression, as we are considering the m value as a square value, it never turns 0. It becomes a very low value which is very nearer to 0, but it doesn't equal to be 0, like it is not 0. It is something like nearer to 0, not exactly 0. That's why the stiffness is reduced here. The stiffness, like from here to like, the stiffness reduces. But we have to understand here about lasso regression. Now let's understand about lasso regression. Lasso. Lasso regression. In lasso regression, most of the things are quite similar comparative to ridge regression. The only difference is here the squaring is not done. Here this value, m value, is not squared, so we do not have to implement square here. We have to use the magnitude of m, or the magnitude of slope. slope magnitude has to be calculated. But in ridge regression, this will be something like slope square. In lasso, the square will be taken out. It will be simply slope. So here it will be like m, lambda into m. If there are multiple features, suppose different features are there, so we have to consider like m1 plus m2 plus m3 plus like that. Like that it has to be multiplied with lambda. Let me clear, lambda is a positive value which is greater than 0. Lambda could be anything and which is greater than 0. But while explaining this algorithm, let me make it very clear. We have to find out lambda value, and the process of finding out lambda value is quite different. For that I will be creating a separate video, and that is known as cross validation. So this lambda value will be calculated by using cross validation method. For that I will be creating a separate video. So we can see here like the slope magnitude is used, or ultimately if there are separate m values are there, m1 plus m2 plus like that, it has to be used. But the question is like, what is the similarity? We have understood the similarity here, as well as we are getting here the sum of residuals, as well as the lambda value is considered, and all the features will be added and multiplied with lambda, and the calculation has to happen. So if the value is appearing, whatever the value is appearing, based on that we have to like understand what will be our best fit line. Best fit line we have to understand. The question appears, why this lasso? If it is so similar, why we cannot use a single? Why, if it is quite similar, why we are not using ridge? What is the special quality of lasso regression, and how it is different? Difference is, if in ridge regression the squaring is happening, that's why this m value never turns to 0. It is not equal to 0. It is somehow equivalent to 0, or the value is nearer to 0, like point something 1, 0.12, 0.23, like this, but it is never equal to 0. As the m value is not equal to 0, that's why the feature remains in calculation. The feature remains in calculation, which results, suppose there are 100 features are present. Suppose there are 100 features are present in a data set. We have to consider all the 100 features while using ridge regression. But in lasso regression, what happens? Suppose here m value reduces. If m value reduces, it turns to 0. Suppose there are 100 m values are present, like 100 features are present. Out of 100 features, suppose there are some 60 features for which m value is equal to 0. For that, suppose m1 is having value, m2 turns 0, then m3 is like we can see here, m3 equal to value, and m4 is also value, m5 is equal to 0. Like this, if something happens, like if this series continues up to 100, like we can have like m1 plus m3 plus m5 plus m7, m6 and m8, m9, like this. This m2 will be omitted here, m4 will be omitted here, and m7 will be omitted here. Like this, the features which are equal to 0, that will be omitted out of our calculation. So which results, we will be having only those features which are essential for us. Unnecessary features will be omitted, which is nothing but feature selection. So ultimately, lasso regression is helping us in feature selection, which is quite advantage in lasso regression. But if most of the features are quite relevant for us, that time we can go for ridge regression. If there are so many features and we are not sure how many features has to be selected, that time we can go for lasso regression. This is what the similarity and difference in ridge and lasso regression. Hope we have understood the topic. I have explained it properly. If any question is there, you can put it in comment box, and very soon I will be uploading all the demo for all the algorithms, and I will be uploading once I start showing the demo. That file has to be uploaded into GitHub. You can get it from GitHub. As currently I'm not having the system, so I'm not able to show the demo for these algorithms. We will be working on some different data sets once I start showing demo. Next we will be proceeding for a different algorithm, and I'll be uploading a separate video for different algorithm. One of my viewer has put a question on comment section regarding ROC curve. Let me tell you here, if he is watching this video, he can clearly understand. He has asked question about ROC curve, how ROC curve works. For that I'll be creating a separate video, and as that is a part of classification problem, so all the statisticals and mathematics I'll be explaining you regarding ROC curve, and I hope you understood the video properly, understood the concept properly about ridge regression and lasso regression. Thank you for seeing this video. Please share this video and subscribe to my channel. Thank you so much.